Welcome to Lecture 10. This week we're going to continue our study of calculus. Next week we will not have a lesson. In 2 weeks' time we will finish talking about calculus. This week I'm going to start by talking about the derivatives of the trigonometric functions, the chain rule for derivatives, and then we'll move to the other part of calculus. We'll talk about antiderivatives and integration. First, let's talk about the derivatives of the trigonometric functions. We'll start with sine and cosine. Two rules for you to remember. The derivative of sine is cos, and the derivative of cos is minus sine. Now that we have these rules, we can do things like differentiate y is equal to x squared minus sine x. Let me remind you that if we have a function like this, we can use the sum rule or the difference rule, and we can break this up into two easier derivatives. Derivative of x squared, which is 2x, minus the derivative of sine x, which I've just said is cos x. Or we could differentiate x squared sine x. For this one, we need to use the product rule. We have a function x squared multiplied by another function sine x. So what we do, first we differentiate the first function and we leave the second function just as it is. And then we do plus, and then this time we leave the first function as it is and we differentiate only the second function. Again, the derivative of x squared is 2x and the derivative of sine x is cos x. So we get our solution, 2x sine x plus x squared cos x. Or we could do a quotient rule question. Differentiate sine x divided by x. Now the rule is u prime v minus uv prime over v squared, where u is the function on the top and v is the function on the bottom. For the product rule, we have a plus. For the quotient rule, there's a minus here. So it's differentiate the function on the top, that's sine x prime. The function on the bottom, we just leave as it is, so just x. And then minus function on the top, leave it as it is, differentiate the function on the bottom, so derivative of x, and then divide by x squared. So x cos x minus sine x divided by x squared. Or differentiate 5x plus cos x. This time we use the fact that the derivative of cos is minus sine. So this is 5 minus sine x. Or differentiate sine x cos x. Another product rule question. Differentiate sine, leave cos as it is, plus, leave sine as it is, differentiate cos. We get cos squared x, and then minus sine squared x. Differentiate cos x over 1 minus sine x. This is a quotient rule question. And again, we use the fact that the derivative of sine is cos, the derivative of cos is minus sine. So derivative of cos gives us minus sine, and then the function on the bottom we leave as it is, 1 minus sine x. Minus, leave cos x as it is, and then differentiate 1 minus sine x to get 0 minus cos x. And on the bottom, 1 minus sine x all squared. Now, we always want to simplify as much as we can. We have a sine squared plus cos squared. And I think almost everybody knows sine squared plus cos squared is just 1. So we're left with 1 minus sine x on the top and 1 minus sine x squared on the bottom. Cancel one of these and we're left up with the answer 1 over 1 minus sine x. Next, the tangent function. Another rule to learn, the derivative of tan is sec squared. Now, this one I'm going to prove to you, and I'm going to prove it to you using the quotient rule. Why the quotient rule? Because tan just means sine divided by cos. So it's a function divided by a function, and we know how to differentiate sine, and we know how to differentiate cos. That's derivative of sine multiplied by cos minus sine derivative of cos divided by cos squared x. So cos squared x plus sine squared x on the top, that's just 1 over cos squared x, but that's of course exactly the same as sec squared x. And the other three, the derivative of sec x is sec x tan x, the derivative of cotan x is minus cosec squared x, and the derivative of cosec x is minus cosec x cotan x. All three of these can be proved using the quotient rule, just as I just did to prove that the derivative of tan was sec squared x. You could use the same method to prove any one of these. Sometimes we like to ask one of these on the exams, and sometimes we don't ask it. I suggest you practice these just in case this is one of the years where we do ask it on the exam. We might ask it, we might not. For example, find y double prime if y is equal to sec x. So we need to take sec x and we need to differentiate it 2 times. Now differentiating 1 time is easy. I've just said the derivative of sec is sec x tan x. Then we need to differentiate it again. Y double prime is going to be the derivative of sec x tan x. We need the product rule. That's the derivative of sec x, and then you leave tan as it is, plus leave sec x as it is, and then differentiate tan. What's the derivative of sec x? It's just sec x tan x. I've just said that. What's the derivative of tan x? It's sec squared x. We're left with the answer sec x tan squared x plus sec cubed x. Our second chapter from today is about the chain rule. How do I differentiate something like sine of x squared minus 4? That's a function of a function. We use a rule called the chain rule. First of all, we need to make sure that our functions are both differentiable in the right places. So to start with, I'm just being careful. Then f composed with g is differentiable, and the formula is this. The derivative of f composed with g is f prime at g of x multiplied by g prime of x. But I think it's easier to remember if we use Leibniz's notation. If we use Leibniz notation, the chain rule says dy dx is equal to dy du dx. And that's easy for me to remember because I imagine that the du's can somehow cancel out with each other and we're left with dy over dx. That's not really what happens, but I like to remember it like that. So for example, let's do this one. Differentiate y is equal to sine of x squared minus 4. We have a function of a function. We have y is equal to sine u, where u is equal to x squared minus 4. We know how to differentiate these two easy functions. dy du, of course, is just cos u, and du dx is equal to 2x. Chain rule says we just need to multiply these two things together. The chain rule says dy dx is dy du du dx. So that's just cos u multiplied by 2x. Change it around, 2x cos u. But we can't have u in our final answer. We want x in our final answer. So substitute in again, and we'll end up with the final answer, x squared cos x squared minus 4. In mathematics, if we use a rule, we need to say what, or theorem, we need to say what rule or theorem we're using. So somewhere in the answer, it's a good idea to write by the chain rule if we want full points. If we forget to write by the chain rule, we're going to lose 1 or 2 points for this question. Differentiate sine of x squared plus x. First, we need a u. To use the chain rule, we need to choose a function to be u. So the first part of our answer is let u be equal to x squared plus x. Then by the chain rule, d dx of this function is the same as d du of sine u du dx. We know how to differentiate sine, it's just cos. We know how to differentiate x squared plus x, that just gives us 2x plus 1. So the answer to this question is 2x plus 1 multiplied by cos x squared plus x. And again, at the end of your answer, just write by the chain rule to get full points. Sometimes we need to use the chain rule more than once. This time we're going to need to use the chain rule 2 times. Differentiate tan of 5 minus sine 2t. First thing we do is we choose a u. Let u be 5 minus sine 2t. Then our function gt is just equal to tan u, and we know how to differentiate tan. So by the chain rule, dg dt is the same as dg du du dt. So that's just sec squared u multiplied by d dt of 5 minus sine 2t. But how do we differentiate 5 minus sine 2t? We need to use the chain rule a second time. We need a new variable, we need to use a new letter. I've already used u, so let's choose a different letter. Doesn't matter which letter we choose. I'm choosing to use the letter w. Let w be equal to 2t. Then let's continue. d dt 5 minus sine 2t is then the same as dw of 5 minus sine w dw dt. And we can do both of these derivatives. ddw of 5 minus sine w, of course, is just minus cos w, and dw dt is just equal to 2. We don't want a u and we don't want a w in our final answer, so we replace those back by functions of t to get our final answer, minus 2 cos 2t sec squared 5 minus sine 2t. Let me just repeat myself. Your final answer should not have a u or w in it. Make sure you put X or T or whichever letter you're using back in before you finish. There's a special type of chain rule which we can use for powers of a function. Let me remind you, the chain rule which says dw dx is dw, so dy dx is the same as dy du dx. If y is equal to f of u, that's the same as saying d dx of f of u is equal to f prime of u du dx. But in the next section, we're not interested in just any function f, we're only interested in power functions. We're going to be talking about what do we do if f of u is equal to u to the power n. Well, then of course f prime is just n u to the power n minus 1. So the chain rule for powers of a function is d dx of u to the power n is equal to n u to the power n minus 1 du dx. In the next few examples, we're going to be using the formula in the box at the bottom of this slide. For example, d dx of 5x cubed minus x to the power 4 all to the power 7. We have a function to the power 7. So using the chain rule, we have a 7 at the front, and then we decrease the power of 7 to 6. And then we also need to multiply by the derivative of the function we have inside the bracket. So multiply by d dx of 5x cubed minus x to the power 4. Let's do another one. D dx of 1 over 3x minus 2. This is a power of a function because this is just d dx of 3x minus 2 to the power minus 1. So what do? We write the minus 1 at the front. Then we decrease the power by 1. From minus 1, we go down 1 to minus 2. And then we multiply by the derivative of the function we have inside the brackets. So multiply by d dx of 3x minus 2. There's a typo here, I think. That should be a 3. D dx of sine to the power 5x. So let's do the same thing. We have a 5 at the front. We decrease the power from 5 to 4, and then we multiply by the derivative of sine x. So the answer is 5 sine to the power 4x cos x. Differentiate the absolute value of x. What we're going to be using is the formula absolute value of x is the square root of x squared. Does that make sense? Let's think about it for a moment. What if we have x is 2? then x squared is 4, and the square root of 4 is 2. What if x was minus 3? Then x squared is 9, and the square root of 9 is 3. Yes, the square root of x squared is always the same as the absolute value of x. Okay, so using this formula, and we're going to be assuming that x is not 0, because this function is not differentiable at 0. We're going to differentiate the square root of x squared. So that's d du of the square root of u multiplied by d dx of x squared. We can do both of these derivatives. The derivative of square root of u is just 1 over 2 square root of u, and of course the derivative of x squared is 2x. We end up with x over square root of x squared. In other words, x divided by the absolute value of x. Does that make sense? Let's look at the graph. This is a graph of the absolute value of x. Let's suppose this is 2. At this point, we would have 2 divided by the absolute value of 2. 2 divided by 2 is 1. So the slope here is supposed to be equal to 1. Yep, that makes sense. What about if we were at minus 3? Then it's minus 3 divided by the absolute value of minus 3. Minus 3 divided by 3 is equal to minus 1. The slope over here is equal to minus 1. Yes, that makes sense. Let y be equal to 1 over 1 minus 2x cubed for x not equal to a half. Show that dy dx is always strictly positive. Okay, well, first thing to do is to calculate the derivative. We have a power of a function. We have some function, in this case 1 minus 2x, and then it's to the power minus 3. So minus 3 at the front. Decrease the power by 1. From minus 3, we go down 1 to minus 4. And then we multiply it by the derivative of the function. Derivative of 1 minus 2x. We end up with 6 over 1 minus 2x to the power 4. Now, 6 on the top is a positive number. On the bottom, we have 1 minus 2x to the power 4. Any number to the power 4 is always strictly positive. So we have positive number divided by positive number. We always have a positive number. Next idea, I want to answer the question, why do we use radians in calculus? Remember I said the derivative of sine x is equal to cos x, but that's true only if we use radians. What happens if we use degrees? So just a quick recap. Looking at the picture at the top, that's a semicircle of radius 1. We can see here the angle inside is 180 degrees, and the distance around the outside of half a circle is pi. So 180 degrees is the same as pi radians. That means 1 degree is the same as pi divided by 180 radians, or x degrees is the same as pi x divided by 180 radians. So now I want to differentiate sine x degrees. And what that really means is the derivative of sine of pi x over 180. We have the chain rule now, so we know how to differentiate that. And we can see that we get pi over 180 cos pi x over 180, or pi over 180 cos x degrees. So that means we actually have two formulae. We have a nice formula if we use radians. If we use radians, it's just derivative of sine is cos, easy to remember. If we wanted to use degrees, the formula is derivative of sine x degrees is pi divided by 180 cos x degrees. And that's not very nice. And if we were differentiating lots of times, we would get lots of pi's divided by 180, and our calculation would get too complicated. This is the reason for why we use radians in calculus. Chapter 30 is about antiderivatives. This is the idea of doing the opposite of a differentiation. Capital F is an antiderivative of f on an interval I if the derivative of capital F is equal to small f for all x in the interval I. So for example, 2x is the derivative of x squared. So that means if we swap these two functions around, x squared is an antiderivative of 2x. We have the idea of doing the opposite of finding the derivative, going the other way. If small g is equal to cos x, then an antiderivative of small g is capital G is equal to sin x. Why? Because if we differentiate capital G, we get small g. Cos x is the derivative of sin x. Change that around. Sin x is an antiderivative of cos x. We can add antiderivatives together just as we would derivatives. If 2x plus cos x is small h, then an antiderivative is x squared plus sin x. Now, I've been saying an antiderivative. Note that x squared is not the only antiderivative of 2x, because, for example, 2x plus 1 is an antiderivative of 2x. Why? Because the derivative of 2x plus 1 is 2x. So the derivative of x squared plus 1 is 2x. And x squared plus 5 is an antiderivative of 2x, because if we differentiate x squared plus 5, we get 2x. x squared minus 1234 is an antiderivative of 2x because the derivative of x squared minus 1234 is 2x. We could have any number here. It could be plus 1, plus 5, minus 1, 2, 3, 4. Put any number here that you want, and we would still have an antiderivative. We can write this as a theorem. If capital F is an antiderivative of small f on some interval I, then the general antiderivative, that means all of the antiderivatives, is capital F plus a constant c. So, for example, find an antiderivative of 3x squared that satisfies capital F of 1 is equal to minus 1. First, let's just find any antiderivative. X cubed is an antiderivative of f because the derivative of x cubed is 3x squared. As soon as we know one antiderivative, we can just do plus c to get the general antiderivative. The general antiderivative must be just x cubed plus c. We haven't finished yet because we haven't satisfied the extra condition. We want to have f of 1 is equal to minus 1. So we're going to need to choose the correct constant c. So I'm going to start with this. I'm going to start with f of 1 is equal to minus 1, just written the other way around, just so it's neatly in this line. F of 1 is 1 cubed plus c, or 1 plus c. What value of c can we choose so that minus 1 is equal to 1 plus c? We can choose c is equal to minus 2. So the answer to this problem is x cubed minus 2. Let's just run through some of the simple functions, then their derivatives and their general antiderivatives. Let me just repeat the previous idea. So I want to have f of 1 is equal to minus 1. That's what the question tells us that we need to have. So I'm starting with that just here. I've written it in the blue box. I've just changed the order of it round. I know that f of x is x cubed plus c. So f of 1 must be 1 cubed plus c, which is just 1 plus c. So I need to have minus 1 is equal to 1 plus c. Which value of c makes this true? C equal to minus 2 makes this true. So the answer must be x cubed minus 2. Okay, so let's forget about e to the power kx. I think I've taken that out of this course. The derivative of x to the power n is nx to the power n minus 1. The derivative of sine kx is k cos kx. Derivative of cos kx is minus k sine kx. Now antiderivatives. Let's look at x to the power n first. If we differentiate x to the power n, we do two things. We decreasing the power of x by 1 and we're multiplying by n. What's the opposite of decreasing by 1? The opposite of decreasing by 1 is increasing by 1. And what is the opposite of multiplying by a number? The opposite is dividing by the number. The general antiderivative of x to the power n is x to the power n plus 1 divided by n plus 1 and then plus c. We can just check this by differentiating it. What do we get if we differentiate x to the power n plus 1 over n plus 1 plus c? We multiply by n plus 1. We decrease the power of x from n plus 1 to xn. And the derivative of c would just be 0. N plus 1 on the top and n plus 1 on the bottom will cancel, and we just end up with x to the power n. Next, look at sine and cos. If we differentiate cos, we get minus sine. What's the opposite? The opposite is finding the general antiderivative of sine. We go backwards. We end up with minus cos. The opposite of multiplying by k is dividing by k. So the general antiderivative of sine kx is minus 1 over k cos kx plus c. Next, the general antiderivative of cos kx. The derivative of sine is cos, so go backwards, go the other way. The general antiderivative of cos will be sine. Instead of multiplying by k, we divide by k. So 1 over k, sine kx, and then always plus c. We have a sum rule and a constant multiple rule for antiderivatives as well. Suppose capital F is an antiderivative of small f, suppose capital G is an antiderivative of small g, and suppose that k is just a number. The sum rule says the general antiderivative of small f plus small g is capital F plus capital G, and then at the end we just tack on plus c. The constant multiple rule says the general antiderivative of kf is k capital F, and then just put plus c at the end. For example, find the general antiderivative of 3 over the square root of x plus sine 2x. We have 3 multiplied by a function plus a function, where the first function is x to the power minus a half, and the second function is sine 2x. I want to find antiderivatives of g and h first. An antiderivative of g, we know how to do this. Increase the power by 1 and then divide by this new number. So x to the power minus a half plus 1 divided by minus a half plus 1. And we end up with 2 square root of x. We need an antiderivative of small h. The derivative of cos is minus sine, so changing that around, an antiderivative of sine is minus cos. because it's not just cos x, it's cos 2x, we also need to divide by 2. So minus a half cos 2x. Then we can put it all together. We can use the sum rule and the constant multiple rule. If small f is 3g plus h, then capital F is going to be 3 capital G plus capital H. So 2 root x, and then we're going to multiply that by 3, and then we're going to add on minus a half cos 2x, like this. And then at the end, don't forget this, always plus c at the end. We have another name for the general antiderivative of f. It's also called the indefinite integral of f with respect to x. And we can write it like this. There's this stretched letter s, f of x, and then dx. Dx tells us that we're integrating with respect to x. This stretched letter s is called the integral sign. The function that we're trying to find the general antiderivative of, or the indefinite integral of, is called the integrand. And the dx on the end tells us that x is the variable of integration. So some simple ones that we've done before. The indefinite integral of 2x, that's the same as the general antiderivative of 2x is x squared plus c. The indefinite integral of cos x, the same as the general antiderivative of cos x, is sin x plus c, always plus c. And we could add these together. The indefinite integral of 2x plus cos x is x squared plus sin x plus c. Calculate the indefinite integral of x squared minus 2x plus 5. I'm going to solve this 2 times. Let's suppose we know an antiderivative of this integrand. Let's suppose straight away we can see that because the derivative of x cubed over 3 minus x squared plus 5x is equal to this integrand, we could just write down the answer x cubed over 3 minus x squared plus 5x plus c. That would be a correct answer. Or we could solve this a different way. If maybe we had a more complicated function, we might want to split this up into some easier problems. We could split this up into the indefinite integral of x squared minus the indefinite integral of 2x, and then plus the indefinite integral of 5. And we could do each one of these separately. So we would get x cubed over 3 plus a constant, and then minus x squared plus c2, x squared plus a constant, and then plus 5x plus a constant. Rearrange that x cubed over 3 minus x squared plus 5x plus constant minus constant plus constant. But remember, we only need one constant. We don't need to have 3 constants when we integrate. We only need to have one. C1 is a number that we don't know. C2 is a number we don't know. C3 is a number that we don't know. So altogether, they just represent some number that we don't know. We can give that a new name. We can call all of this number that we don't know C. And then we can write the answer like this. We don't need to go through all the effort of having separate constants. As long as we understand that we just need one constant, we could always just add on plus c at the end. Next example. You drop a box off the top of a tall building. The acceleration due to gravity is 9.8 meters per second squared, and you can ignore air resistance. How far does the box fall in 5 seconds? Here's a picture. This is you at the top. And here's your box, which you're dropping. We're going to let ST denote how far the box has fallen in t seconds. We're going to use the letter V for velocity. So, the question tells us the acceleration is 9.8 meters per second. But acceleration is just the derivative of velocity. Or to change that around and say it another way, velocity is an antiderivative of acceleration. What's an antiderivative of 9.8? An antiderivative is 9.8t. What is the general antiderivative? 9.8t plus c meters per second. What can we say about the constant c? Well, we're told that you let go of the box at time t equal to 0. So that means at time t equal to 0, the box is not moving. In other words, the velocity at time 0 must be 0. But then that just means that the constant is 0. So far we've found that the velocity at time t must be 9.8 t meters per second. We want to find the position. But velocity means derivative of position or derivative of displacement. So the distance fallen is an antiderivative of velocity. An antiderivative, or I should say the general antiderivative of 9.8t is 4.9 t squared plus c. That's 9.8 t squared divided by 2. We need to find this new constant. Again, you're told that you let go of the box at time t equal to 0. So that means in 0 seconds, the box has fallen 0 meters. S of 0 is 0. But then the new constant is also 0. So the answer to this problem is S of t is 4.9 t squared meters. So after 5 seconds, the box has fallen 4.9 multiplied by 5 squared, or multiplied by 25, or 122.5 meters. And that brings us to the final chapter for today's lesson. Before I start the final chapter, would you like a 10-minute break? Anybody else like to vote? Okay, more people want a break than don't, so we're going to take a 10-minute break. And let's continue. Chapter 31 is about integration. Integration is about areas underneath a graph. For example, what is the area of this region which I'm calling R? That's the region which is underneath the graph y is equal to 1 minus x squared between the x-axis and the y-axis. Well, we could approximate this using two rectangles. I could draw two rectangles inside using the right-hand side of the rectangle to determine the height. So, for example, I could draw a rectangle of height 3/4 and width 1/2, and a rectangle of height 1/2 and width. So height 0 and width 1/2. We can calculate the area of rectangles easily. The area of these two rectangles, height multiplied by width, so 3/4 multiplied by 1/2, and then plus the other one, plus 0 multiplied by 1/2. We get 3/8 or 0.375. Can we do better than this? The answer is yes. We could use more rectangles. Let's suppose instead of using two rectangles, I want to use 4 rectangles. Again, there's a rectangle of height 0 here. That's why I'm saying there's 4 rectangles here. How do I calculate the heights of these rectangles? Well, what is this point, for example? At this point, x is equal to 1/4. And remember, y is equal to 1 minus x squared. So that's 1 minus 1/16, which is 15/16. So the height of the first rectangle is 15/16, the height of the second rectangle is 3/4, and the height of the third rectangle is 7/16. The height of the fourth rectangle is 0. We can calculate the area of these 4 rectangles, and we can say that the area of the region R, that's the area that we really want to calculate, is approximately equal to the area of these 4 rectangles. The first rectangle had height 15/16 and width 1/4. Multiply those two numbers together to get the area of the rectangle. The second rectangle had height 3/4 and width 1/4. Again, multiply those numbers together. The third rectangle was height 7/16, width 1/4, and the fourth rectangle was height 0, width 1/4. When we calculate this, we get 17/32, or 0.53125. And this was better than just using 2 rectangles. In fact, every time we increase the number of rectangles we use, the total area of these rectangles gets closer and closer to the true area of R. We could do it, say, with 16 rectangles. And I'm not showing you the full calculation, but the area of these 6 rectangles is 0.63476. And that's getting closer to the area of R. We're not quite there yet, but we're getting closer. We can get closer and closer if we keep increasing the number of our rectangles. So we want to do a limit of a finite sum. The idea is this. Step 1, we're going to take the interval between 0 and 1, that's the bottom, and we're going to chop this up into n pieces, and each one of these pieces is going to have a width of 1 over n. Here we are, chop it up into lots of little pieces. And then on each one of these little pieces, we're going to draw a rectangle. Like this. And these are all drawn so they fit inside the region R in this example. And then we're going to take the limit as n tends to infinity. Okay, looking at this picture, let's look at the red one, the first one. The red rectangle has a corner at this point, and I hope you can read this. It has a corner at the point 1 over n, f of 1 over n. That means the height of this rectangle is f at 1 over n. And of course, its width, we've said, is going to be 1 over n. The widths are all the same. What about the green one? The green rectangle must have height f at 2 over n and the same width, the width of 1 over n, and so on. The first rectangle has area 1 over n, that's its width, multiplied by f at 1 over n, that's its height. The second rectangle has area 1 over n, f at 2 over n. The third rectangle has area 1 over n, f at 3 over n, and so on. We're going to add these all together using sigma notation. The area of n rectangles is going to be the sum from k is equal to 1 up to n of the area of the kth rectangle. Just add all of these areas together. In other words, we have the sum of 1 over n, f at k over n. We need to get a formula from this, and then we're going to take the limit. So let's see what we can do. Remember, our function is 1 minus x squared. So f of k over n is 1 minus k over n squared. Multiply that by 1 over n, we get 1 over n minus k squared over n cubed. We can split that up into two sums. The sum of 1 over n minus the sum of k squared over n cubed. The first one is an easy sum because the first one is just 1 over n plus 1 over n plus 1 over n plus 1 over n and so on. In the first one, we just have n multiplied by 1 over n, which of course is just 1. Let's look at the second term. The 1 over n cubed, we can take that outside because n is a constant compared to the sum. 1 over n cubed multiplied by the sum of x squared. Think all of the way back to the start of the course. We had a formula for the sum of the first n squared numbers. And the formula that we had was n plus 1, 2n plus 1 divided by 6. This is where we need it. This is why we did it all of the way back at the start of the course. We need it here. The area of n rectangles is 1 minus 2n squared plus 3n plus 1, all divided by 6n squared. We want to take the limit of this function as n tends to infinity. And we've talked about limits, so I'll leave this for you to check. The limit of this function is 2/3. That means if we approximate the area of the region R by n rectangles, and then we increase the number of rectangles all of the way to infinity, the area of these n rectangles is going to have a limit 2/3. Or to say it another way, that means that the area of the region R is going to be 2/3. That's the idea of integration. We're approximating the area under a function by some rectangles, and then we're going to take the limit. Let's do it for a more general function. We'll generalize everything in this section. Let's suppose we have a function f, which is sometimes positive, sometimes negative. Let's suppose f is defined on the closed interval from a to b. We're going to cut this closed interval into n subintervals. And this time, the pieces don't have to all be the same size. It doesn't matter. In each one of these subintervals, we're going to choose one point, and we're going to call that ck. The width of each one of these little pieces, each one of these subintervals, we're going to call capital delta xk. So looking at the picture at the bottom, the width for the first one is delta x1, the width of the second one is delta x2, the width for the third one is delta x3, and so on. Somewhere in the middle, we have an interval I'm calling the kth interval. The width is delta xk. And in each one of these intervals, we're going to choose a red point and call them C1, C2, C3, etc. The red points are going to decide how tall these rectangles that we're going to draw are. On each one of these little pieces, we're going to draw a rectangle of width, delta xk, and height, f at ck. So here we are. Here are our rectangles. Now, sometimes the rectangle is under the graph, sometimes the rectangle has a part of it which is outside the graph. That's fine. We're trying to be as general as we can. If the function is negative, then we have these rectangles which go downwards. So we have these rectangles which we think have negative height and therefore negative area. That's okay. That's what we want. We're going to add together the areas of all of these rectangles. Here we are, the total area of the n rectangles, where rectangles which go up have positive area and rectangles which go down have negative area, is the sum from k is equal to 1 to n of f of ck delta xk. This is called a Riemann sum for f on the closed interval from a to b. Then we want to take the limit as the number of rectangles tends to infinity, or if we want to be more precise, we want to take the limit as the maximum width of the rectangles tends to 0. Sometimes this limit exists, and sometimes this limit does not exist. And that's what we will be talking about in the next lesson. Next week, we do not have a lesson. In 2 weeks' time, we will talk about the definite integral. That's the limit of the Riemann sums. We'll talk about the fundamental theorem of calculus, the substitution method, and how to find the area between curves. Are there any questions?